Thank you for attending my presentation on hyphenated parallel FTIR and mass spectrometry for unambiguous component identification in complex samples. Today I'll briefly introduce spectrometrics and the DiscovIR-GC technology before moving on to an overview of applications and wrapping up with the rest of the DiscovIR family. Spectrometrics is a boutique consultancy and analytical solutions partner with a collaborative approach to consultancy, training and bringing new and emerging analytical technologies to the UK and Ireland. Despite being a mature technology, DiscovIR-GC is a relatively new hyphenated technique to most chromatography and mass spec users. It is therefore useful to introduce concepts in familiar terms. Separated components are deposited onto a reusable cooled zinc selenide disc, which is about the same size as a compact disc or DVD. Under default deposition speeds, a full-scan infrared spectrum is acquired every 0.6 seconds. Up to 40 hours of chromatography can be deposited in a spiral track, which is recorded in a similar way to the groove on a vinyl record. The 3D data structure is similar to GCMS, comprising a base peak chromatogram and high-resolution structurally informative FTIR spectra for each scan. To the user, the main noticeable difference to GCMS is the routine use of contour plots in data exploration. As with GCMS, spectral libraries can be searched, though the higher selectivity and specificity of solid phase IR spectra allow unambiguous identification. Where unknowns are not in the library, the DiscovIR can be combined with mass spectrometry to aid partial or complete structural elucidation. Furthermore, the disc is indexed, allowing rescanning or over-deposition to increase signal to noise of the entire deposited chromatogram, or, in the case of rescanning, specific chromatographic regions. Whilst the DiscovIR does give a concentration-dependent response, it is typically installed with parallel analog and/or mass spectrometric detection. This schematic provides a more detailed illustration of the principles on which the DiscovIR-GC operates. The GC column passes into the vacuum chamber of the analyzer, indicated by the dotted black line, through a heated interface. The column eluent is then deposited onto a rotating infrared transparent zinc selenide disc. Deposition occurs through condensation of the vapor phase analytes onto the disc, which for GC applications is typically cooled to -40°C. A focused infrared beam, which enters the vacuum chamber through salt windows, then passes through both the disc and the condensed sample, after which it is refocused onto an MCT chip in the detector, with a solid phase infrared spectrum being collected at approximately every half a second. Condensing the eluted peak provides several advantages over the older light pipe technology. Firstly, converting the eluted peaks from the gas phase into the solid phase greatly concentrates the sample and increases the sensitivity of the technique. And secondly, at 4 reciprocal centimeters, solid phase spectra deliver superior selectivity and specificity compared to gas phase spectra. At this stage, it's worth focusing on the deposition onto the zinc selenide disc in a bit more detail. At 10 centimeters in diameter and 2 millimeters thick, it's slightly smaller than a DVD or compact disc. In this illustration, the green spot represents a peak that is condensing onto the disc, which is rotating counterclockwise. As the disc rotates, the deposited peak moves towards the infrared beam. As the deposited peak passes through the beam, the instrument records solid phase transmission spectra, and the entire chromatogram is deposited onto the disc as a continuous track. As the disc is indexed, it is possible to rescan deposited peaks or over-deposit repeated injections of a sample. Both approaches increase the detection limits attainable with low concentration samples by improving the signal to noise. Signals are additive, noise cancels out. If we move from schematics to a photograph of the vacuum chamber, the capillary is located on the right. As components elute from the column, they're deposited onto the rotating zinc selenide disc, recording in a similar spiral manner to the groove on a vinyl record, using liquid nitrogen to condense the GC eluent. Transmission IR analysis is then done in real time on the deposited track. There are several reasons to choose DiscovIR-GC. Ultimately, they all derive from the fact that, compared to mass spectrometry or gas phase FTIR, every compound has a unique solid phase infrared spectrum. This means that library searches are unambiguous. In addition, FTIR is the only spectroscopic technique with commercial libraries of similar size and coverage to mass spectral libraries, and many customers will have libraries of their own raw materials and finished products. This allows routine, unambiguous identification, even for structural, positional, and diastereoisomers, where a reference spectrum for the compound exists in the library, even in complex mixtures and complex matrices. Furthermore, for unknowns, infrared spectra contain structural information that can be combined with mass spectral information, including molecular weight, formula, and fragmentation data, for partial or complete structural elucidation. For many applications, mass spectrometry is the right tool for the job. But direct deposition, hyphenated FTIR, is a powerful technique to add to the toolbox where unambiguous identification is required, or for the identification of compounds in complex mixtures or matrices. I'd like to illustrate the power of the DiscovIR-GC using a simple worked example, the identification of xylenes and ethylbenzene. The mass spectra are both virtually indistinguishable and simple. They do, however, contain important useful information. We can determine the molecular formula from the molecular ion and isotope pattern, and the base peak at mass 91 confirms the presence of a benzene ring. We can therefore conclude that all four spectra are alkyl substituted benzenes with either one ethyl or two methyl substituents. In this case, the FTIR spectra are in the libraries, and at 4 reciprocal centimetre resolution, the spectra can be readily differentiated with library search algorithms. And there are key differences in the fingerprint region too, that allow the contribution of co-eluting pairs to be determined. But let's imagine we didn't have FTIR. What would the alternatives be? Well, we could do preparative GC, concentrating and collecting fractions for NMR. Or we could buy or synthesize the 4 possible isomers and co-inject them to confirm a retention time and mass spectral match, provided, of course, we're using a separation that yields baseline resolution of all the isomers. In this example, both approaches are comparatively straightforward, as there are only 4 possible candidates. But if we move to monoterpenes, increasing the size of the carbon skeleton by just 2 carbons, for each molecular formula there are tens to hundreds of possible isomers, many with virtually indistinguishable spectra, only some of which are in commercial libraries. Here, even with multidimensional chromatography, any identification is only partial, and there's a significant possibility of misidentification. By comparison, searches against GCIR libraries are still partial, but they are unambiguous. It is also worth noting that IR spectra can be accurately predicted from structures using artificial intelligence such as neural networks and machine learning. The first 2 application areas, forensic drugs and defence and security, account for approximately 80% of the DiscovIR-GC install base. They largely target compound applications where the uniqueness of FTIR spectra delivers advantages in enhanced burden of proof and improved selectivity and specificity compared to mass spectrometry. The former is paramount in the International Chemical Warfare Agent Monitoring Programme, where the combination of FTIR and mass spectrometry delivers the extraordinary evidence required to prove extraordinary claims of prescribed weapons use beyond all reasonable doubt. For forensic drug analysis, the DiscovIR-GC has been adopted by police, border and customs agencies worldwide. It is mainly being used to identify designer drugs and novel psychoactive substances, and in drug seizures where GCMS doesn't provide the selectivity and specificity needed to satisfy SWG drug guidelines. The addition of parallel, solid phase FTIR meets the enhanced requirements for 2 category A and 1 category B technique in a single run. Whilst the first 2 applications were primarily target-based, the use of the DiscovIR-GC by the chemical ecology community highlights its capability as a powerful technique for structural elucidation. Chemical ecology involves the identification and characterization of infochemical communication between and within species. Here, the challenge is in the fact that the volatilome contains biologically active infochemicals, in a complex mixture of inactive metabolites. Typically, their analysis involves a mixture of GCMS, preparative GC with analysis of the fractions by NMR, and bioassay-based GC with electroantenography using scalped insect antennae as detectors. Even annotating the inactive metabolites is challenging. There are over 30,000 known naturally occurring terpenoids, the most common class of infochemicals. So even with comprehensive multidimensional GCMS, peak annotation using commercial libraries containing only 5,000 spectra cannot confirm an identification. With DiscovIR, the library matches are unambiguous, and for unknowns, combining DiscovIR with mass spectrometry is a powerful platform for de novo identification in a single instrument. The conventional infochemical workflow shown here comprises GCMS plus GC-EAD followed by preparative GC at NMR of the isolated natural infochemicals at submicrogram quantities. With multiple injections required to obtain enough material for proton and 2D NMR and days of NMR acquisition time for each component, studies are slow, expensive, and challenging. With DiscovIR-GC, the workflow can be redefined. Many components can be unambiguously identified from library matches. And for unknowns, DiscovIR-GC with parallel mass spectrometry of the entrained and microderivatized extracts allows structures to be proposed and shortlisted without preparative GC. It's only necessary to synthesize and analyze the leading candidates for a confirmatory retention time, FTIR, and mass spectral match. And as only the commercial or synthetic compound requires confirmatory NMR, with milligram quantities available, even a 2D NMR is fast. Groups that have adopted the DiscovIR-GC platform benefit from faster, significantly lower cost, and easier studies. Taking an example from the literature characterizing moth pheromones, approximately 20 new infochemicals were found. And although the EI spectra allowed group classification and tentative identification as a series of novel fatty acid isoprenyl esters, the mass spectra lacked sufficient information for full structural elucidation, and the majority were not present in commercial libraries. Taking the conventional approach to metabolite identification, it would have taken several weeks to complete preparative GC on over 20 metabolites, and up to a week per metabolite for comprehensive NMR studies. By contrast, combining GC with parallel FTIR and MS with whole sample microderivatizations allowed FTIR and mass spectra to be obtained simultaneously. FTIR of the underivatized entrained extract guided microderivatizations to confirm both the double bond position and isoprenyl group identification. The DiscovIR-GC also allowed confirmation of the double bond isomerism prior to synthesis and confirmatory GC with parallel solid phase FTIR and mass spectrometry. As with terpene analysis, GCMS is a great tool for the routine analysis of well-characterized samples. However, due to the large number of potential structural and positional isomers yielding similar mass spectra, unambiguous de novo identification typically requires advanced derivatization, and even targeted analysis can be complicated in biological or environmental matrices. Adding solid phase FTIR allows unambiguous identification based on equivalent chain length, FTIR and mass spectra. Qualitative and quantitative group classification can be done from the FTIR spectra too, and unknowns can be assigned to existing classes, and spectra are structurally informative, yielding direct and derived information on functional groups, chain length, isomerism and more. For both FAMEs and terpenes, the combination of retention data, mass spectrum and FTIR spectra deliver enhanced Metabolite Standards Initiative Level 2 metabolite ID. For example, for FAMEs, the chain length can be derived from the ratio of the methylene group and carbonyl peak group, and the degree of desaturation can be determined from the shift in the carbonyl peak. The figure on the right shows group classification of trans fatty acid methyl esters from a 37 FAME mix using extracted waveband chromatograms. In summary, there are a range of benefits to adding DiscovIR-GC with parallel mass spectrometry to the analytical toolbox. For target compound identification, its selectivity and specificity improve confidence in both identification and automated peak annotation. This delivers both improved productivity and time and cost savings. For unknown identification, streamlined workflows reduce or eliminate preparative chromatography and can potentially free up NMR capacity too. And there's more to discover beyond gas chromatography. The DiscovIR-GC delivers advanced characterization of natural and synthetic polymers, including excipients, in raw materials and finished products. And the new DiscovIR-LC is set to deliver a paradigm shift in the analysis of small molecules, including natural products and metabolite identification. Thank you for watching this recording. If you have any questions, please don't hesitate to contact me by email or using the contact form on the Spectrometrics website. Thank you.